distribute. This is a merge operation. So these are like the situations I'm looking for. It's like, okay, here's my empty node. I've got a 3 node over here, 2 node over here, then I'm going to change it to that. So there's all these kind of if cases that you go through when you want to do this. It looks complicated, but honestly, if you sat down with some paper and just looked at it, you know, kind of sketch it through, you would say, okay, now I have to deal with this case. I have to deal with the case where I have a 3 node over here, my parents a 2 node, then what is it going to look like when I'm done? And you'll say, oh, I just have to change a couple pointers, move a couple values. So then you write the 5 statements or whatever to do that. Then you say, all right, what about in this case? And then you write a few statements. So it's a little bit tedious, but it's not terrible. And then if you, all right, so the reason we don't use 2-3 trees is because we like 2-3-4 trees better. So since someone said, well, I started with the BST, and you know, I just changed the rules a little bit and let myself have 2 nodes and 3 nodes, and look, it stayed balanced all the time. So that was a 2-3 tree. Let's do another one. Let's do 2-3-4 trees. And so with the two,
talk about 2-3-5 trees.
we'll get there. So we've got a long night still, and we might get all the way up to 2-3-20. All right. So it would be 2, 3, 4, 5, 6, 7, 8, 9, yeah. So it would be a little bit longer. Yeah. So 2-3-4 trees are like 2-3 trees, except for look at these guys. We have 4 nodes. A 4 node has 3 values and 4 children. And nobody has no children. I mean, no children for leaves. Sorry, this one doesn't. You're right. But nobody has 1 child still. We still have the no 1 child rule. It's like the opposite of China. It's the no 1 child rule. So, but we can have these 4 nodes now. So the 2 node, a single data item, and it has that same less than greater than. 3 nodes, and then 4 nodes has 4 children, and it satisfies the same basic idea of smallest, small, middle, large, middle, or large, and then largest. Right? I mean, it's this. It's hard to say, it's easy to visualize. So this is smaller, and 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 this. So again, it's harder to say than it is to visualize, and it intuitively, again, makes sense, right? They just stay in order. Okay. So, doesn't so I repeat a few things here because I really want you to get it. We might end up early. I say that a lot, and we never end up early, so don't put too much stake in it. We might end a little early today. 2, 3, 4 trees. Why do we want 2, 3, 4 trees? It actually turns out that the insertion and removal operations are actually more efficient. So you already noticed that the 2, 3 tree, the insert algorithms and the remove algorithms had a lot of these extra steps and was kind of complicated. And you might not have thought it through, but if you realize, or if you think it through a little more, you realize it's a 2-pass system. You're going down recursively to find where the thing ends up being inserted, let's say, and then you recursively have to come back up doing work. Splitting nodes as you come back up. Delete was the same issue. You go down until you find what you need to delete, and you have to come back up merging those. So it's 2 passes, down and then back. So it turns out with 2, 3, 4 tree, we don't have to do 2 passes. We only do 1 pass, which I'll explain how we get there in a little bit. But we only need to do 1 pass. So more efficient. It does have greater storage requirements because you have to have multiple pointers. I mean, you have to have 4 pointers instead of 3 as a max. So searching and traversing a 2, 3, 4 tree, I don't have to go through those algorithms again. It is really just an extension of what we use for the 2, 3 tree. So just kind of talk through it kind of quickly. I'm searching for an element in a node, and let's say it is a 4 node. Yeah, 4 node. If the small, medium, or large is the value I'm looking for, then I'm done. I found it. But if it's not, and the value is less than small, then I go down that one. If it's between small and medium, I go down that one. If it's between medium and large, I go down that one. If it's greater than large, I go down that one. It just recursively calls the next one down. So that's how I would do a search. So traversal, the in-order traversal is exactly the same thing, right? I visit this, then me, then this, then me, then this, then me, then this. So pretty straightforward. Okay, now one of the things I don't like is in this presentation is they didn't give us a whole lot on the insert algorithm, but they give us some. Here's the trick. Inserting in 2, 3, 4 tree, I told you it's one pass because the insertion algorithm splits a node by moving up its item to its parent node. But they didn't say here, but it does say in the book. Oh, well, okay, here. Splits 4 nodes as soon as it encounters them. When it's going down the tree looking for the node to insert, remember you insert at the leaf. As you're going down the tree, if you're ever on the way to the leaf where you're going to insert, if you hit a 4 node, you immediately split it. Split it, push the parent up, or middle guy up. And you keep going, okay? Now, when I hit a 4 node, it's got 3 values. I can split it. It's got 3 values and 4 children, right?
Page 17.
So it's this kind of deal. I've got 3 values, S, N, L, and I've got 4 children. I'm going to split this node by taking the M, the medium guy, moving it up to the top. And this becomes small and large. These children hang off those just like they naturally would. And M goes up to the parent. And then these guys hang off both sides of M. So all the order is maintained. And M goes up to the parent. Now, the parent, if the parent was a 2 node, is there room for it? Yeah, because it was a 2 node, now I can add another value. And I either add it to the left or the right of the value. It's already there. It doesn't really matter. It's easy to figure out. If the parent was a 3 node, is there room for it? Yeah, because it becomes a 4 node now. Right? It becomes a 4 node. And again, I can figure out where it goes.